everyone, before we begin, I would like for you to look at these two lists and think about how the two lists differ. So when we look at the first, temperature, distance, height, area, volume, they seemingly have no connection. Area and volume, maybe, distance, height, maybe, but then there's temperature. How do all of these relate? These five measurements are solely magnitudes. Meaning it's just a number. So temperature, it can be 23 degrees Celsius. Distance, it could be 5 miles. Height could be 5 inches. Area could be 26 square feet. And volume could be 33 cubic millimeters. So these are all magnitudes. We're just a size. Like I said, a size or a scale is a good way of saying it, okay? Whereas force, velocity, and acceleration, if you have little experience with physics, you might not know what these have in common. But force, velocity, and acceleration, these have both magnitude and direction. Okay? So we are focusing on this category. In this category, we can title it, as you can see here, these are vectors. Examples of vectors. Okay, so let's talk about vectors just for a little bit, some basics here before we actually get into working with them. First thing is that there's one form that a vector can take, and that form could be AB. And we have these pointed brackets. These pointed brackets signify that we have a vector. Now this is the component form of the vector. And we'll talk about why we call it the component form of a two-dimensional vector. Okay, so let's imagine we have a Cartesian plane, XY axis, and we have this component form. What this represents is that this vector, whatever we are talking about, goes from, we'll say the origin here, and it goes to a point, an actual coordinate of A comma B. Okay, now this vector is more of a direction, saying the horizontal component we go right A and then vertically B. And we represent vectors by using directed arrows, meaning you can say geometrically it's a ray, but we actually say directed segment with the arrow there. So two things make up a vector, as we said, both direction and magnitude. When we say magnitude, we are actually focusing on the length of this vector. So the length of the vector is the magnitude. And then when we look at the direction of the vector, it's the direction that the arrow is pointing. So how do I write this? The direction of the vector is the direction of the directed arrow. Okay, and we're going to elaborate more on that as we get further and further into this unit dealing with vectors. So just know that vectors are made up of both a magnitude and a direction, and that we have this form, the component form. So some examples of vectors is 5, 2, -1, 4, or 0, 6. Here we would just be a vector going vertically, 6 units. And then negative 2, 0, here we would be going left 2 units and no vertical movement. So if we had a vector, say that was 0, 0, this actually has a specific name. This is the 0 vector. Okay? The 0 vector has no length and no direction. So that's something important for us to know. All right? So, dealing with some definitions, we have a couple definitions in this lesson. The head minus tail rule. This is more of how do we find the component form if we're given the ends of the directed arrow. Okay, so the definition we're going to write here is if an arrow has an initial point, say x1, y1, and a terminal point, meaning an endpoint, of x2, y2, it represents the vector. Okay, so we're using our special brackets for vectors. It represents x2 minus x1, comma, y2 minus y1. So if I have the ends of the vector, we find the difference of them, and they're the components. Here it is very important that the terminal point, the end of where the vector is going, is placed first in this calculation. Okay? Otherwise, you'd be saying the vector goes in the opposite direction, and that is very important here to be careful of how you're placing your numbers in. All right? So, I should say this as well, moving back up here. When we name a vector, typically if you look in textbooks or other resources, they use bold letters, bold lowercase letters. What you're going to see me use throughout this lesson and future lessons is, let's say we want to call this vector V. Okay, so I'm going to write the V's a little special. I'm going to do a V and then an additional bar to the side, almost as if I'm going down, up, and then down again. Okay, so that's how I'm writing the V for vectors, and you'll see how I'm writing other letters like U and whatnot here. Okay, so let's see what we have next. So let's say, great question. Show that this arrow from R to S is equivalent to the arrow from P to Q. So looking at this, I can do this graphically. We want to show that these are equivalent vectors. There's really magnitude and direction, but there's a way we can do without finding all of that. So if I were to graph this real quick, just doing a rough sketch because I don't have the grid available. Let's see, so we need to do negative 4, 2. So negative 4, 2, could that be R? And then negative 1, 6. Okay, so that would be S, and that would be one vector. And then let's imagine we have positive 2, negative 1. Okay, that would be P. And then positive 5, positive 3. Okay, and this would be Q. So we desire to show that these two vectors are equivalent. So if I want to do R to S, remembering that with R to S, that the terminal point must be considered as my x2, y2. So when I go to do this, I'll be taking negative 1 and subtracting negative 4. And then 6 subtracting 2. So doing the calculation real quick, we find that the component form of this vector is positive 3, positive 4. All right, and then 4 P to Q. So again, same thing, since Q is the terminal point, it gets placed first in this calculation. So 5 minus positive 2, and then 3 minus negative 1. Okay, 5 minus 2, 3 minus negative 1. And because the component forms are the same, we can say that these two vectors are equivalent. And just like that. So what if the questions change slightly? So we've looked at how we can show that they're equivalent. What if I'm asking, what if I give you the vector and only one point of the directed arrow? If P is the point for negative 3 and P to Q represents this vector, find Q. So what I'm really saying here is 2, negative 4 is what we should get. Now the Q, we're looking at the naming of the arrow. Q is the terminal point. So we don't know x2. We subtract 4, that'd be x1. And then we don't know y2 either. And that would be subtract negative 3. All right. Now, if you understand the component form of the vector, we can say that this must equal 2. So if 2 must equal x minus 4, well, we could argue then that x2 equals 6. And then I can also say that negative 4 will equal y2, really plus 3, which would say that y2 must be negative 7. So then the coordinate of Q must be, to have this vector, it must be 6, comma, negative 7. Okay, so just understanding vector form, the component form, and knowing which coordinate you're finding, just very simple algebra. Okay, moving on. So, talking now, we looked at definitions and just the basics of vectors. But what if we're looking at the vector magnitude? So I have a definition already here for you. Let's see what it says. If the vector, notice how it's written, a little extra bar. If it's represented by the arrow from x1, y1 to x2, y2, then its magnitude, the bars around the vector name, these bars represent that whatever is after it is the magnitude or the length of the vector. Now this should look very familiar. So we're saying to find the magnitude of a vector, we are really using the distance formula for the two ends. That's it. Distance formula gives us magnitude, gives us length. And if I'm given the vector in component form, if I already know what my horizontal movement is and my vertical movement is, then the magnitude is simply you take your horizontal component, square it, you take your vertical component, square it, and square root that value. And that gives us the magnitude. So let's try this out on an example. I have two examples here. So find the magnitude. A vector v by p to q, where p is negative 3, 4, and q is negative 5, 2. So it's distance formula. So I want to find the vector, or the magnitude of v. We square root. Let's see, go on the q, so we have negative 5 minus negative 3. Okay, plus 2 minus 4. And doing the computation there, you'll find that you'll get 2 squared plus 2 squared. So we could say the magnitude is square root of 8. The magnitude of the vector from p to q is square root of 8. No approximation, it's just the exact. So looking at an example where we have it in component form. These are really nice because I can say here it's u. Notice how u is written differently. I can say the magnitude of u, I just do a u, by the way, with an extra little piece on the front side. Magnitude of u is going to be the square root of negative 1 squared plus 3 squared. Really nice, really straightforward, really simple. So we get 1, we get 9, which would give us square root of 10. Okay? So magnitude, length, really comes down to the distance formula. Relating to something you guys already know. So moving on. We're building on what we have talked about so far, just basic definitions. What is a vector? How to find the vector's magnitude. So now we can look at performing operations on vectors. So let's say we have two vectors, u, which is the components u1, u2, and v, which is v1 and v2. So what if we want to find the sum of two vectors? What do you think we're going to do? So if I have one vector and its components are u1 and u2, and a v and it's v1 and v2, the sum of the two vectors, well, we find the sum of the components, which would say that the sum here is going to be u1 plus v1, and then u2 plus v2. That's it. If I want to add the vectors, I add the components. All right? We call this, by the way, the end result. We call it the resultant. That should sound familiar, right? Talking about forces and previous lessons, we look at the resultant we get from the sum. Now, if I wanted to find the difference, it's the same thing. The difference of two vectors is the difference of the components, u1 minus v1, okay? That's sum because saving space. So what if I wanted to find the product? Notice here I said product with the scalar, meaning number. If I want to take one number and multiply a vector by it, what do you think we're going to do? Well, let's write this down. So k times u1 comma u2. What do you think we're going to do? If you're thinking distribute, yeah, it's going to be k times u1 and k times u2. That's it. There's no name for this. It's just, you can say it's a scalar vector because we're simply enlarging it or shrinking the original. So giving you visuals here. Visuals are always nice to have. Let's see. Okay, so let's talk about the sum. So if I have some vector u and some vector v, its sum, thinking the parallelogram approach, that's where we imagine we're shifting or sliding this one vector over. And doing the same here. The sum of the two vectors, if I wanted to add these two vectors together, the resultant will be this vector. So you could try to just make two vectors. You do this yourself, make two vectors, and then add them together, and what you get will be this vector. The coordinate, the directions you get will take you to here. So now if I had a scalar, a product, so I imagine if I had for a moment vector v, and I wanted to have a scalar of 1/2, that would take me to right here. The direction did not change, just the magnitude. Okay? So let's end here with some examples. So if I had vector u to be -1, 3, and vector v to be 4, 7, what would its resultant be? Now, resultant we reserve the word resultant for sum. So if I want to add the two vectors, what would its component form be? So you can pause the video now and actually try these three problems and see how you do. Okay, so how'd you do? I mean, it's really straightforward from adding two vectors. Like I said previously, you add the components. So adding u and v, we added the x, you could say the horizontal components, and the vertical components here, we get the resultant. Then with the scalar, we take the 3, we thought of it as distributive, and we multiplied that by through. And then we had this other expression where we looking at scalars and then combining them. So I distributed and then combine them together, the components, to give us -6, -1. And that is it. So this is your initial, possibly your first time seeing vectors. We had a couple definitions here, looking at sum, the product with a scalar number. And so I wish you the best of luck when you practice this, and I'll see you in the next video.